of x. We did some graphs, looking at a graph and trying to graph the derivative, and then the last example I did was from a graph trying to approximate the derivative, which that one was like that number 1 on the homework assignment. So you're just trying to draw a tangent line at each point and estimate the slope. The next piece that I want to talk about is what it means to be differentiable. When we see this term, differentiable just means the derivative exists. Okay, it is possible to be differentiable on different intervals. You can be differentiable between two numbers, less than a number, greater than a number, or everywhere on a graph. So let's take a look at this one. If I want to figure out where this function is differentiable, that means the derivative has to exist, right? With the absolute value, what have we done every time whenever I gave you an absolute value? Yeah, we made our two equations. We did the piecewise. So we know it equals x if x is greater than or equal to 0, and it equals the opposite of x if x is less than 0. So that's what we've done since the first week, and we will continue to do. Every time we see an absolute value, we write it in those pieces. So I want to see where this function exists, and there's really three pieces I need to consider. I need to consider positive numbers, negative numbers, and 0, and see if we have a derivative. So case 1, let's look at our positive numbers. So if x is greater than 0, then the derivative is the limit as h approaches 0, f of x plus h. If x is greater than 0, you're on the first piece. So if you plug in x plus h in for x, you just get x plus h minus f of x all over h. Your x's cancel, you're left with h over h, which is 1. So what is the limit as h approaches 0 of 1? 1. Okay, so we have found the derivative exists for all positive numbers, and that derivative is always 1. Okay, so it's differentiable for positive numbers. Now let's check for negative numbers. So the derivative, when you do f of x plus h, if you're talking about negative numbers, we are on the second piece, so it would be the opposite of x plus h. Minus f of x would be the opposite of x over h. Okay, so this would be negative x minus h plus x. So the x's drop, I have negative h over h. Limit as h approaches 0 of negative 1 is negative 1. So it's differentiable for positive numbers. It's differentiable for negative numbers. Now what about 0? 0, I put the equal to on this one, but wouldn't it be the case for either of these, like the absolute value of 0 is 0, it's also the opposite of 0? Those are both true. Do you get the same answer on both of these? No, one gave us 1, one gave us negative 1. If you graph this derivative, what you find, if x is greater than 0, you get 1 out the whole time. If x is less than 0, you get negative 1 out the whole time. Does it exist at 0? No. So, it is not differentiable. At x equals 0. Because those left and right hand limits don't match up. Okay. So let's talk about what this means and if there's a way I could have known it would be differentiable without necessarily doing all this work. In general, if you are differentiable at a point, it has to be continuously. Okay, so if I gave you a graph like this, could this graph be differentiable at 0? Is it continuous at 0? No. If it's differentiable, it has to be continuous. So if it's not continuous somewhere, you will automatically know the derivative doesn't exist at that point. Now, the converse is false. Knowing it's continuous doesn't mean that there is a derivative there. If you think about the absolute value graph, it's continuous at 0, but did the derivative exist there? No. So what we know so far is if the original graph is not continuous, then the derivative doesn't exist. So that's one thing we can look for. Let's see what else. In our absolute value, at 0 it wasn't continuous, and the reason is because of that sharp corner right there. In general, if you have a corner, it's not differentiable there because it's not a unique tangent line at that point. You know, if I give you a curve, there is only one perfect tangent line that only hits that graph at one point. But if I give you a corner, I could draw a lot of different lines that only hit that graph at one point. So, if you have a sharp corner, there is not a derivative. If there is a break in your graph, it's not differentiable there. So, kind of following along that discontinuity piece, if you're looking for at tangent lines, if you have a vertical tangent line, that's a place where the graph isn't continuous, so it's automatically not differentiable there. So the graph I'm just kind of showing you, here's a graph, it's hard to tell, there's so many lines here, but that blue one was the actual graph, and those pink ones are all the tangent lines, and you see as you're coming into the vertical tangent line, it doesn't exist. This function, where it has a very sharp decline that continued for a long period of time, that actually also creates a vertical tangent line. Just your regular x cubed, you don't have to worry about it, but if you just had like a sudden drop off like that, that could create it. So this is the big thing, this slide right here. The 3 ways for a function to not be differentiable. If you have a corner, a discontinuity, or a vertical tangent. In those 3 scenarios, we say that there is no derivative. It's not differentiable. Questions on that? The last piece I want to look at today are higher derivatives. So we've done the first derivative. We can do second, third, fourth. We can keep going as long as we wanted here. Notation, you could have the d dx, that was one of the notations for derivatives. So you could have the derivative of the first derivative. Typically, notation-wise, I will either say something like this, d squared y over dx squared, or a lot of times I might call that y double prime or f double prime of x. So those are the notations that I will stick with the most often. So I want to practice one of those. I believe we did the derivative of this one yesterday in example 2. So in example 2 yesterday, we found that the derivative of this function was 3x squared minus 1. I want the second derivative. So basically all that means is you do the derivative twice. We already did the derivative once yesterday, so I'm not going to recreate that part. Let's do the second derivative. So that is the limit as h approaches 0. When you do f of x plus h, you are plugging it into this derivative equation right now. So f of x plus h would be 3 times x plus h squared minus 1 minus f of x, which in this case is the derivative, it's the thing we're doing the derivative of, all over h. So if we squared this, we would have FOIL and distribute the 3, we get 3x squared plus 6xh plus 3h squared. You guys okay with how I did that? Minus 1. Distribute the negative through this, so that's minus 3x squared plus 1. This is going to be a great one. Okay, so the 1's drop, the 3x squareds drop. You can cancel an h out. So you get 6x plus 3h. So if h goes to 0, we just get 6x. Yeah, you basically, if I asked for the third derivative, we would just do the derivative of this thing. So you just keep working with it. Yeah,
where'd you get the 3x squared minus 1?
We did that one yesterday in example 2. We did the first derivative of it, and that was the answer we got. Other questions? In general, if it's a polynomial, each successive derivative should get prettier and shorter. That is not the case if you are dealing with something other than a polynomial. So if you have radicals or fractions, that is not going to get prettier as you go along, but the polynomials will. So just talking a little bit, the second derivative is basically the slope of the tangent line in the first derivative. So if you think about it, the first derivative tells you the rate of change of the function. So the second derivative tells you the rate of change in the derivative. Okay. We will talk more about that in the next chapter. We'll start looking at the graphs and how this is all connected and piecing it all together. But we're just kind of starting with this right now. We've talked about position problems a lot. S of t is your position. What's the derivative of position? We've done that one a lot. You did it on the homework assignment you turned in yesterday. Derivative of position is, starts with a B, velocity. The rate of change of position gives you your velocity. So the derivative of velocity, acceleration. Okay, so you think about position. How your position changing is giving you essentially your speed. How your speed is changing is giving you your acceleration. You guys may not have heard this one before. Have you ever talked about jerk in any of your science classes? Okay. The derivative of acceleration is jerk. We will usually just stick with these first three, but I thought I would put that last one up there in case you'd ever seen it before. We can can do third derivatives, so y triple prime or f triple prime. For third derivatives, you know, sticking with the same notation, I'll probably use one of these. After third derivatives, we don't really do tick marks. So if I wanted like a 7th derivative, I would just say like y and put a 7 up here. So first 3 we do tick marks, after that we just write the number. I won't give you 7 yet. Not until I teach you the shortcuts for how to do derivatives. Okay. So let's go back to that function that we were doing. So example 6, we did the second derivative. So we know in example 2, we found f prime to be 3x squared minus 1. In example 6, we got the second derivative to be 6x. Let's do the third derivative. So it is limit, so h approaches 0, f of x plus h. So you are doing the derivative of the f double prime, so that's what we're plugging it into. So 6 times x plus h minus f of x, which is just your 6x, all over h. We get the limit, so h approaches 0, it's 6x plus 6h minus 6x all over h. What happens there? 6x drops, you're left with 6h over h, which is 6, and the limit as h approaches 0 of 6 is 6. I also asked what a fourth derivative. You notice since it was a polynomial we started with, they are getting a little bit easier each time. So the fourth derivative, if we do the limit of that, limits h approaches 0, f of x plus h, if it's just a constant, still 6, minus f of x is all over h. So you get the limit of 0, which is 0. Questions? Do you understand the concept of higher derivatives and how you calculate them? Just keep doing the derivative of your previous answer. Okay. So, all I have left on here, I picked problems out of the book similar to some of your homework questions. So we did that number 2 yesterday. I just want to walk through a couple others that are similar to homework, and then I'm done for today. We did that one yesterday. So number 6. Okay. I didn't copy the directions over, but what I want you to do is sketch the derivative of this. So, first thing we look for when we draw the derivative, is there anywhere the derivative will be 0? Right here you have a horizontal tangent line, so that derivative should be 0. Now these are flattening out. You've got a horizontal asymptote, so those slopes are approaching 0, right? So those should be very close to 0, but not equal to 0. Is this section going to be positive or negative? Positive. So it's got to be positive. We're starting out with those. They are close to 0. But then you notice, if you were to draw these tangent lines, what's happening to these lines right here? They're getting pretty steep, aren't they? So that means my derivative would have to go up and then come back down and hit my point. So we had a horizontal tangent, so it's getting close to 0. At some point, if I could draw, it's going to kind of spike up because my graph itself started increasing, and then it would come back down. On the other side, all of these should be negatives. this is pretty steep, so that means it's actually got a curve to it, but then it's flattening out, so it should be approaching 0. So something like that. Okay, we are just doing very rough sketches. That problem number 1 is the only one where I want you actually like trying to approximate the slopes of the tangent lines. I just gave you one question like that, so you kind of got a feel for it. The rest of these, we are just rough sketching how it would look. Is that one okay? Number 14 here. This graph from the U.S. Department of Energy shows how driving speeds affect gas mileage. Fuel economy is measured in miles per gallon. Speed is in miles per hour. So we've got our mileage, fuel economy here, and our speed there. What is the meaning of the derivative? Okay, you guys have to be able to tell me what the derivative is. It is a rate of change, yes. So our derivative is the rate of change in, think when you do slopes, it's y over x, so it's in y, which was my fuel economy. With respect to my x, which was speed. So basically it tells me how the fuel economy is changing in terms of a given speed. Part B, I want to draw the derivative. Okay, do we have any horizontal tangent lines here? So those happen at like a max or a minimum. This is kind of a max, isn't it? Maybe not perfect, but where does that happen? 55-ish. Okay. Until then, this is pretty steep, so that's going to be kind of high. All these are increasing, so they're positive. Then it's flattening out, so it should be getting closer to 0. So we're going to start, coming up, and it's just going down, kind of flattening out to 0. Then this section is decreasing, so that tells me it is negative. Does it ever start flattening out? No, so it's not ever really coming back to 0. It's just kind of looking like that. Okay, very, very rough sketch here. C. At what speed should you drive if you want to save on gas mileage? 55 miles per hour. Yep. Because you could look at that a couple different ways. The easiest might be if you just look at your graph. That was the maximum. That's the highest fuel economy that you got. So even just looking at the original graph, that might be the most obvious there. Questions on that one? You're going to have some that ask you to tell where a function is not differentiable. Remember we had that slide, I put the stars on it, and I told you 3 things that make it not differentiable. So I want the x value and I want to know y. What would be the first one? Y. Yeah, you could really give me 2 options. You could say it's discontinuous there. It also kind of appears to have a vertical tangent line, so if you told me either of those, it would be okay. You wouldn't have to give me both. Okay, where else would this be discontinuous? Where is the derivative not differentiable? Y. You could just say corner, sharp corner. Anywhere you have those corners, you don't have a derivative. that one is kind of more of a judgment call. So it appears at 5, it looks like it's dropping off. It could be going turning into a vertical tangent, but I didn't really give you the full graph. So that one I would take either way. If you list it at x equals 5 because it appears to have a vertical tangent, that would be great. I probably wouldn't count that wrong if you didn't include that one. That's the other thing. It's kind of hard to tell exactly where it would happen because I just kind of stopped the graph. So it's probably, oh, that's at 5. This would be a 6, sorry. But it does appear if you were drawing those tangent lines, they are becoming more and more vertical. So assuming that graph followed that same pattern, I would assume that probably is a vertical tangent there. Unless it were to change patterns at some point. Okay, questions there? I want you guys to take a look at this last one before we go over it. So, it's kind of a confusing mess, but there are 4 things here. There is an original function, a first derivative, a second derivative, and a third derivative graph. I want you to see if you can figure out which might be which. Typically, if they're polynomials, your original function is probably going to be the one with the most curves in it, the most maxes and mins in it. If it's not a polynomial, it doesn't necessarily follow that rule. But which one appears to have the most curves to it? D. Okay, let's start there. So I just kind of make myself a list and try to put these things in order. So I know D, start looking. It's got a max here and here. So the derivative should hit 0 twice. If I look, this one hits 0 both of those places. This was increasing, so derivative should be positive. Decreasing, so derivative negative. Increasing, so derivative positive. So can we be confident that C is the derivative of D? Okay. Let's talk about C now. So C only has one tangent line right here. So the derivative can only hit 0 one time. So it's either A or B. Here the derivative was, or the function was decreasing, so the derivative needs to be negative. Then increasing, so derivative positive. So which one would that be? B. All right, let's look at B. So this one only has one horizontal tangent line, and it's right there at 0, kind of where it flattened out. It wasn't a true max or min, but it is still a place where the tangent line would be 0. Which really, I guess, A and D both have that property. This one is increasing the whole time, so its derivative should always be positive. So that would be A. So we did pick properly the first time. F is, or the original function is D, first derivative C, second derivative B, third derivative A. Any questions for me? Okay, so you guys have a lot of time right now. Tomorrow is going to be mostly a work day, but we are going to do a quiz on Friday, so I will take part of tomorrow to do some quiz review. It's just over 2 sections, section 7 and 8, which section 7 is really more of this stuff. So this assignment is pretty good review, but I will do some extra review tomorrow, and then you've got time to look.
I won't be here tomorrow.
Tomorrow? Okay. Then really you're missing the work day. I will